Hello and welcome back. We will finish off the solid discussion with the final two acronyms, I and D. Pardon me. And then we will have one more quick video on refactoring, but let's first finish off solid. So just a quick reminder that we covered the single responsibility principle, the open-close principle, and the Liskov substitution principle in the last video. We discussed what they are, how we can sort of see a violation, and what code that is adhering to those principles might look like. So now we're going to jump right in with the interface segregation principle. So the interface segregation principle is effectively segregate your interfaces. Clients shouldn't be forced to depend on things that they don't use. So if I don't need 8 different ends coming out of my USB, they should not all be here. Don't force the client to depend on things that they don't need and that they don't use. And this is really best sort of exemplified with an example. So imagine for a second that you were writing code for like a mechanic app, like you'd be able to book appointments online and check out what services you want to allow the user to use, right? So imagine that, a mechanic company, they come to you and you build them this application, and the services that they offer are oil change, tire rotation, car wash, checking car pressure, changing snow tires, vacuuming the interior, and fixing the windshield of a vehicle. And it's a really great application. It goes over really well. The company is really happy. And you realize that you could actually package up your back end and sell it to another company that has their own application that wants to be able to also use bookable services. Imagine that this is something kind of like the Jane app, if you've ever used that, which lots of like local small companies use in order to sort of allow you to pick from bookable services online. Now, it's a violation of the principle because what we saw was if an individual company that only does oil, like 15-minute oil changes, or a car wash company comes along, they get stuck forced to implement one way or another all of the different pieces, right? They have to have access to these, like the tire rotation service and the glass repair and the oil and the cleaning. All of it gets brought in, even if they're not using all of those endpoints. So instead, what can we do? We can actually separate these out nicely into multiple interfaces, and then depending on the company's needs, they can just bring in the pieces that they actually need. So this is actually a really, really simple interface, a really, really simple principle, and really sort of easy to understand and fix. So it sort of ties in nicely with single responsibility principle. Yes, originally we had this idea of an iMechanic interface, but we can certainly see that there are different categories that maybe fall underneath mechanic. And here we are, we've got like tire behaviors, glass repair, oil behaviors, and cleaning behaviors. So pretty simple to sort of adjust and make this work for a more diverse set of applications. Our last principle here is the dependency inversion principle. Often maybe is mistaken for, people will call it dependency injection principle. We'll see why in a minute, but I just want to make sure I'm really highlighting the name, dependency inversion principle, because we're going to invert the dependencies. So effectively, the principle states that high-level modules should not depend on low-level ones. Both of them should depend on an abstraction instead. So like an interface. And the best example of this is the idea that a high-level module, such as a lamp, should not depend on a low-level module, such as the wiring of your house, but rather both are dependent on an abstraction of some kind, i.e. an outlet. We put an outlet in between, and now our high-level modules plug into the outlet, and our low-level module, our house wiring, connects to the outlet, and now these two different modules can talk to each other very cleanly through an interface. This is important because imagine for a second that we have a lamp class, and imagine that the bulb was a halogen bulb and it was directly screwed into the lamp and like soldered into the lamp. So then you really like this lamp, but if the bulb burns out, if you want to switch from a halogen bulb to like a fluorescent bulb, an LED bulb, right? A smart bulb, whatever it might be, you'd actually have to throw the whole lamp out and buy a new one. That's what this code is showing us. In order to change from a halogen bulb, because we are actually initializing it right here inside the constructor. If I want to switch it to an LED bulb, a smart bulb, a fluorescent bulb, I'd have to stop my program, actually change all the code in here, and make a hard-coded change difference. So the most common way to spot a dependency inversion principle violation is within a constructor, having that new keyword. That new keyword within a constructor tells us that we're going to have like a long living instance variable of some kind that has this direct dependency on another bulb, on another class. Now, of course, we still need to initialize it, but how are we going to get around this scenario? Well, effectively, it comes down to interfaces. The fact that I can initialize a new halogen object tells me that halogen is not an interface. It's not an abstract class. And right here, I can see that bulb is defined as this concrete instantiable class. That right there tells us we have the violation. We don't want that to be the case. We probably want a bulb interface, and then we can pass in the type of bulb that this lamp is currently using. So here we go. We make an interface bulb that has a turn on and a turn off class defined or method defined in it. And now we've got fluorescent, incandescent, halogen, all these different types of bulbs, each of which can implement that bulb interface. And now we can just pass it in. So now we keep our lamp, and if we want to change the light bulb, all we do is put a new light bulb in it. No big deal. So like I said, one of the most common ways to solve the dependency inversion principle violation would be with this idea of dependency injection, which is what we're doing right here. We are injecting the dependency. We've changed it to an interface, and we're injecting this dependency right into here. And then this can be any concrete class that implements that interface. So this here is called dependency injection, and this is how we solve dependency inversion principle violations. So with that, let's take a look at an example that I have here. Okay, so here we have a data service.java file, and we can see that we can pretend, I better sort of make this a bit more obvious, persistence layer class. I'm just putting it all in one file for ease. But we have like a data service variable. We have a private MySQL database. Here we initialize it, and we can perform some data operations. Imagine that this method actually exists like presentation or something, right? Presentation layer. Method right there, and all it's going to do is create the data service and perform some operations. And we can pretend like this is connecting to a database. I know it's not right now. All right, so let's go ahead and whoops, there we go. Compile that, and then let's run it. And what we can see happening down here is we perform our database operations, connect, backup, right? Some system.out, disconnect, whatever it might be. We can see that things are happening. Now, great. I'm not even worried about this being tightly coupled to the backup support, although it is true. We are directly connecting to this MySQL database. However, now if it comes time to do some testing, how are we going to test this, right? We're connecting to a database, and there's no easy way for us to disconnect it and maybe just use, like, as we had previously mentioned, some kind of a fake, right? Like an array list, an in-memory database. So what we would have to do is we would have to make an in-memory database. We'd have to come into our code here, change this to be the in-memory database, change this to be the in-memory database, and we probably don't even have like a connect and a backup. Like all of the function calls might look a little bit different. There's just so many pieces here that might be different. So what could we do instead? Well, I've already created it over here, but we have this in-memory database 54 example. So now we've got an interface where each of those methods are defined. Now, my SQL class does not change. The only difference is now I implement this database interface, and then I can go and make my in-memory database and also implement it there. Now, when I come down here, instead of having a MySQL database variable, I'm going to have a database variable. And instead of having a database variable that gets initialized in here, I'm going to pass it in. Database is starting to look weird now. Let's turn Let's rename this here so that I can actually run the code. In memory database 54. Or actually, let's just like leave it for a second. That's fine. I'll just make another class called in memory database 54, just so that we have somewhere that we can run our code. Public static void main. Just get this all set up nice. I'm just going to add some blank lines to pull this up a little because it's kind of like low down. And then we'll go ahead and we'll grab our data service. DS, make a new data service. And we need to now pass something in, right? We need to pass our database in. Well, coming from main, we probably do want to pass in that MySQL database so that we can appropriately perform the data operations that we need. Right, so into our data service operation, we can pass in our database, and now we can use our data service to perform the data operations. This should say public class. Let's run this. Now, at this point in time, this might look still very similar to, whoops. There we go. Sorry about that. So far, this looks very, very similar to what we had previously, right? Only now we just have this extra layer of passing stuff through and an extra interface we're wrapping things in. However, now imagine for a second that we have a class test perform data operations, right? This would have to live somewhere else. I recognize that. This code wouldn't run as is PS. Okay, because it would be like its own class and its own like file for testing things. And this would be like test data services. Okay, and then in here we would have a method. We'd need to bring in JUnit. Public static void. I can't even remember if it's static or not right now. None of these little details matter for this example. Test perform data operations. Now, if we want to run this test, right, we're going to do our arrange, our act, and assert. Depends what we want to assert. Maybe we're going to assert like data put in database, or maybe connection closed from disconnect. Whatever it might be, we have our assert. Our act, as we know, needs to be a data service doing that perform data operation call. And now here we need to set up that data service. New data service. Well, we don't want to connect to the real database. So what we get to do is we get to actually here just call the constructor for the new in-memory database, as opposed to in our actual production main, which called the new SQL database. Our test main can call the in-memory database, and we didn't have to change the code that lived up in here, whereas we did in our previous example. Okay, I really want this to be like in a state where you can run it on your own machines for when I upload this. So let's just Java, let me just make sure that this compiles. There we go. So now we can see that we're connecting just as we did before, just in our old data service, just as it did before. Only now we don't actually have to make any changes like open close principal violation as well to the data service layer, to the database layer. None of that matters. All we do is swap out the difference on the main end, depending on if it's like a test front end or a real front end, right? So we can see how dependency inversion might work. So we've now seen solid violations in lots of different examples, right? Sometimes our code can violate many principles and patterns, and big refactors are a nightmare. So what should we actually be doing? Well, when we refactor our code with solid, we should be taking these small steps. We should add interfaces. We should split our responsibility very slowly, and we should make sure that we're always running tests before we do our refactor and after we do our refactor to ensure that we did not break any functionality. So at this point, you should go and explore your own project. Maybe add an interface to the business layer, or maybe an abstract class to a to a data object if you need them. Those are probably less common, but just in case, right? Take this new abstraction and let's write a truly isolated unit test. So now we can truly isolate from any type of database backend, from any type of front end. Maybe we add an abstract layer to our data object so that we can make a a stub, and we can write like a fakey object underneath that abstract class that we can now be using as part of our test. Let's get as isolated as we can and write this test. Now I've got an example here so that we can really see what it looks like. I will upload it as well, but let's just take 2 minutes to go through it before we close out this video. All right, so this will look very similar to the example I just showed with the in-memory database versus like the fakey MySQL database, but let's just take another look here at what we can do. So I've got a user score manager class that has a logger, a notifier, and a score repository. All of these are getting passed in and set inside the manager. And then our process user file will actually log this information, calculate that base score. It pulls it from the repo, from the database. It'll add some scores. I just wanted some kind of logic in here. And it will also send a notification to the user letting them know, hey, your score has changed. Okay, so I've created all of these interfaces, the notifier, the score repository, the score updatable, right? Interface segregation principle. I've got them all separated, and we can see that the logger has the log function, the notifier has the send notification, the score repository has a fetch base score, and our score updatable interface is in charge of all of those updatable score behaviors. Now, when we go into our user, we'll see that it is implementing that score updatable method. And if we come back to our score manager, we could have a logger, like an actual logger class that implements the logger, a notifier class that implements the notifier, and the score repository class that implements the score repository interface. We will see those in our main in just a second. So in our user, we are doing this score updatable, where we have our string name and our int score, and we implement each of those methods according to what we would have it do. Now, we could have a main method somewhere on a front end, but I didn't write all that up here, right? Here instead, I have scaffolded my user score manager test. So I am trying to write some unit tests for this user score manager. And what I've gone ahead and done is I have created 3 static dummy classes. I have a stub logic that does nothing. This isn't even really a stub. I mean, it's void. So it does nothing. What I could do is, just for my own sanity, have it print stub logger log called. Now it's more of a stub than anything else because it doesn't have simplified logic. It just always does the same thing over and over again. Same with my stub notifier. I could do exactly the same thing where my stub notifier can say stub notifier has fakey notified the user. We can put the username in here maybe. Username. Whoops. With the message. This is getting too long to all be on one line, obviously. There we go. With the message, we'll add the message that's getting passed in. So now we know that we have something maybe coming out of this. It's also a stub. And then we have a stub repo, which passes in a username and returns the predictable stub best score of whatever it is, right? We also here have our fake user, which would implement score updatable, just like our real user did. Just like the real user, but we're not testing our user class because we don't need to. So what we do is we make a fakey user, it is more fakey than stubbed, right? Because it is a fakey user. The behavior is here to be a score plus equals points. We have the get score, return score. We have the get name, and it's always going to return the name fake user. So now here is the test. We've had all this setup that we've done for this unit test. Here's the test. We create all of these fake pieces of logic because we're not testing any of those. All I want real is the user score manager. So I've faked everything, passed all of these fakey objects into my user score manager, and now I can actually test. So this is my arrange. This right here, this is technically arrange 2, I suppose. This right here is my act, where I'm calling the process user function that I actually want to be testing. And now I can go in here, whoops, and I can do my assertion and make sure that process user appropriately updated the user score. So I'm making sure that my manager process user function appropriately called the logic I required, found the information I required, and then I can go ahead and assert that that's what happened. Now, I really am only testing the score update here. If I wanted to test process user entirely, it might make more sense for me to now have put these print statements in here, right? Because now I can actually go and verify. I can redirect the output stream from console to a string, and I can make sure that what has printed is what I expect to my console, to my logger, etc. But because this was originally only test score update, right? That's why these said do nothing. But there's nothing wrong with having it in there either if you're not using it for right now, because this is just like a base. This is very simple. This is still keeping it simple, right? This still adheres to KISS. And perhaps we're going to have more tests in here that might use them, right? So it's not really a YAGNI either. Anyway, we can now see how completely isolating away from all other aspects of our code, the only piece of code that we are actually using from production is the user score manager. All other pieces of our code have been fakied right here within the test class. This is a truly isolated unit test. So go try this in your own code, give it a try, and then we can move on to the final video this week, which is going to be all about refactoring and sort of when you see certain kinds of code smells, how can we go about refactoring it? It won't cover every type, but it is sort of a nice taste of common code smells and their refactors. Thanks everybody, and I'll see you then. Bye.